So how does a network actually learn those millions of filter numbers? Through a loop, and it is essentially the same loop for nearly every model in deep learning. It begins knowing absolutely nothing. Every filter is set to random numbers. We show it a training image and it makes a guess. Early on, that guess is basically a coin flip. It says dog when the answer is cat. Now we measure exactly how wrong it was with a single number called the loss. A high loss means a badly wrong guess. A low loss means it was close. Our entire goal is to push that number down. Then comes the truly clever step, backpropagation. Backpropagation works backward through the network and figures out, for every single weight, how it nudged the loss up or down. Then we adjust every weight a tiny amount in the direction that would have made the loss smaller. One image barely moves anything, but do this millions of times over millions of images and watch the loss curve slide downward. The guesses get better and better and better. Two more tricks make this practical in the real world. The first is data augmentation. Flip, rotate, crop, and recolor your training images so the model sees endless variety and cannot simply memorize. It has to actually generalize. The second trick is enormous and you will use it constantly. It is called transfer learning. Do not start from random numbers at all. Take a network already trained on ImageNet, one that already knows edges, textures, and shapes, and simply fine-tune it on your specific problem. Because it starts with real visual knowledge, it can learn your task from just a few hundred examples instead of millions. All right, enough theory. Let's open a code editor and build one for real. Let's slow down on that first trick, augmentation, because it matters more than people expect. A deep network is greedy. Give it a small dataset and it will happily memorize every image instead of learning the real pattern. We call that overfitting, and augmentation is our main defense. The idea is simple. Take each training image and make many altered copies of it, all still clearly the same thing. Flip it left to right, a cat is still a cat. Rotate it a little, still a cat. Crop in and zoom, still a cat. Change the brightness as if the lighting were different, still a cat. Shift the colors slightly, still a cat. From one photo, we have manufactured half a dozen. And crucially, the label never changes. The network now sees the cat from many angles in many lights, and it can no longer cheat by memorizing exact pixels. It is forced to learn what actually makes a cat a cat. Best of all, augmentation is nearly free. It is just a few cheap transforms on data you already have. It is one of the highest value habits in all of practical computer vision. And now the second trick, transfer learning, which is honestly how almost all real vision work gets done today. Think about what a network trained on ImageNet already knows. Its early layers learned edges, deeper ones learned textures, then object parts, then whole objects. That knowledge is general. Edges and textures are useful for almost any image task, not just the one it was trained on. So why throw it away? Here is the move. Take that pre-trained network and freeze its backbone, lock those learned filters in place so training does not touch them. Then bolt a small new head onto the end, a fresh layer for your specific classes. Maybe healthy versus diseased leaves, maybe your company's products. And you train only that little head. Because the hard part, understanding images in general, is already done, you can learn your task from just a few hundred labeled examples in minutes on a single computer. Notice this is the exact same idea as fine-tuning a large language model. Reuse enormous general knowledge and specialize it cheaply. That is why you almost never start from scratch.